This question is IMC 2023, question 18, and it covers number theory and especially the topic prime numbers. So in this question, it asks how many squares are exactly 4 greater than a prime? And if we just let the prime number as p, as we will always do, then we know that this positive integer called, for example, k would be, we can get this k squared. Square is exactly 4 greater than a prime, therefore p is equal to p plus 4. And if you first see this equation, it would be quite difficult to figure out what you might do next. So we have to use the properties of prime numbers, which is that p would always have factors only 1 and p. Therefore, we can move minus 4 to p, because we can move 4 to the other side. And what we can see is that we can factorize plus and minus equals p. However, we know that p only has factors 1 and p, and we let the k as a positive integer. Therefore, k plus 2 must be bigger than k minus 2. And therefore, k plus 2 would be p, and k minus 2 would be 1, because it can only be 1p or p1. But this one is greater, the left one, therefore we get p and 1. And therefore we get k is equal to 3, then p would be 3 plus 2, which is 5. And that would be the only case. Therefore, the answer would be B. However, we can spot something easier if you run out of time, or for example, you can't figure out how to move the plus 4 to the other side. Another solution would be by just substituting the square numbers. For example, the square number could be 1 squared, 2 squared, 3 squared, 4 squared, on and on. And that would be 1, 4, 9, 16. We know that the prime is 4 smaller than it, so it'd be 1 minus 4 minus 3, this is the p, 0, 5, 12, and on and on. And here we know that minus 3 cannot be a prime. No, this one is a prime, this one isn't. And if we go on and on, we know that ultimately using this would be the answer. However, if you try at least 10 of them, you will spot that these cannot be the case where it's a prime. Therefore, you can figure out B is the answer. This question is IMT 2023, question 23, and it covers prime factorization once again. So this question asks us if we choose 6 different integers from 1 to 9 is inclusive, such that the product is a square, and we get p squared and q squared, where p and q are both positive. So what we can do is, as I've mentioned, we can prime factorize every one of 1 to 9 and see what we get as a product, then get rid of 3 integers because we only choose 6, and we have total 9. And it'll be easier to get rid of 3 than actually choosing the 6. Therefore, let's prime factorize 1, 2, 3, 4, 5, 6, 7, 8, and 9. What we get from 1, it's not a prime number, so we leave it at itself. 2 is a prime, 3 is a prime, 4 is 2 squared, 5 is a prime, 2 times 3, 7 is a prime, and 2 cubed, 3 squared. So as a product, we get 2, 3, and another prime 5, then 7. Let's make more spaces between them. 5 and 7. And let's see how many we have for each of them. 2, we have 1 here. Let's get rid of it when we count them. 2. 1 plus, and then another 2 here. 2 plus another 1, then 3 up here, times 3 to the power of, let's use a different color, 1 here, 1 here, then 2 here. So we get 1 plus 1 plus 2, then let's just space them, 5, 7. So what we get as the remaining prime numbers would be 5, 1 here, then 7, 1 here. So it would just be 1 and 1. So we get 2 to the power of 1 plus 2 is 3, 3 plus 1, then 7 times 3 to the power of 4 times 5, 7. So from here, we have to get rid of 3 numbers from 1 to 9, and it must be a square number, meaning that the indices here, this is the reason we actually prime factorize every one of them, because these ones, 7, 4, 1, and 1, must all be even, because square number must have even indices. Therefore, we have to get rid of these. It's a must because it must be even, and for that to happen, you have to get rid of 5 and 7. So what we get is that we already got rid of 2. We have to get rid of another one. From here, it's right to here. To get rid of 1 here, it must be at least a 2. So that becomes even 6 and 4. Or it could be getting rid of odd numbers from 2, because we got rid of 2 more, meaning we got rid of 3 in total. Or we could either get rid of some 3s, because it would be at least 1 here, must not forget, and can get rid of 1 here. So it's always even, and also on the other side, it's always even. So we have to see what we get rid of as a product. We would get rid of 2, because 7, 2 to the power of 7, 2 to the power of 6. Then we can get rid of 2 to the power of 3 from 7 to 4. And here it would be 2 times 3 squared. However, the last one, we can't make it, because if it gets over 9, then that wouldn't be one of the numbers you can choose from. Therefore, this can't be the case, and these 2 are correct. So it would be first case, second case. From the first case, it would be 2 times 5 times 7 that we get rid of. Second one would be 8, which is 2 to the power of 3 times these. And what we get if we get rid of 1 to 9 from here, we have to get rid of 2, 5, and 7. Therefore, we get 2 to the 6 times 3 is the same, and we get rid of 5 and 7. Second one would be 7 minus 3, 4 times 3 to the 4. And this would be a square of 3 times 3 to the power of 2 squared. And this would be a 2 smaller than it. Therefore, if we say that P is bigger than Q, because if we sum, then it would be the same, we know that P is the first case, Q is this, because we only think about the things inside the brackets, since it's P squared and Q squared that we get. Therefore, P is 72, 36. And P plus Q would be 72 plus 36, which is 108. Therefore, it's D.